New Year's resolution number one, no more 30-minute videos. So we're going to keep this low. New Year's resolution number two, keep these things amazing. And to do that, I'm going to bring in a shot of each Algebro telling you their favorite math joke today. What do you think about that, Sully?
Come on! This
I know,
guy's
right?
crazy!
All right, so we're going to start off with Mr. Brust and then get on to exponential functions.
Hey guys, Mr. Brust from Ramstein. We are the coolest and the bestest. I have a joke to start off the new year. What kind of math did they do during the Civil War? I've been giggling. Lincoln Logs. Everyone have a happy new year. Into my third period class, happy St. Patrick's Day.
Okay, enough of that. Lincoln Logs. That's classic Brust. All right, so exponential functions. We're going to learn what those are. And you kind of already know because you did this in Algebra 2. An exponential function is when the x is in the exponent. So it looks something like, should I draw an example? Let's do an example real quick. Y equals 2 times 3 to the x. See how the x is in the exponent? That's an exponential function. So one of the most common examples that you guys can probably relate to is Moore's Law, which, written by Gordon Moore. He worked for IBM, very smart guy, and he figured out that the processor speeds, or the overall processing power for computers, it doubles about every 18 months. That's crazy when you think about it. Twice as fast every 18 months. That's how much faster computers are getting. I mean, every 18 months, that's like a year and a half. And the flip side of it is that the cost to produce a comparable computer will be cut in half. Again, that's every 18 months. So what we're going to do, instead of making it 18 months, we're just going to round it up to 2 years. That makes our math a little easier. And with the first example, let's suppose that in 1988, this is actually a true story, but in 1988, the number of transistors in this microprocessor, the 386SX, was 275,000. What is the approximate transistor count in 1998? All right, so here's what I want you to do. As it says, every 2 years, we're going to assume every 2 years, it doubles. So you can see I filled in the first part of the table there, 275. It'll go up to 550. You double it. Keep doubling, fill out that table, and then graph it. Pause the video and do all that by yourself. Try and keep this video short. Ready? Go. Pause the video. Okay, so here's what we get when you fill it out. Obviously, we go into the millions in terms of the transistor count. And when we graph it, look, 1988, we're at 275,000, and it gives you this nice nonlinear curve right here. I was going to call it bendy. It's very bendy, but it's a nonlinear curve, and you can see that in 1998, this model would predict 8.8 million and actually 7.5 million. Not too bad. Okay, it's pretty close. All right, next part. All right, so in example 2, it's talking about what it would cost to build a computer that would be comparable. So like in 2002, if you took a $3,000 computer, if that's what it cost in 2002, in 2004, 2 years later, that same computer would only cost $1,500. And then you can see that the cost gets cut in half every 2 years. All right, so in 2014, it would cost $46 to make that same computer, which 12 years earlier cost $3,000. Now, you can tell between the two examples here, see how the first example, it goes up and it goes up and it goes up. Okay, that's called exponential growth because it's going away from both the x-axis and any value down here. It's just growing and growing and growing. In the second example, see how it's getting closer and closer and closer to one specific value. That's called exponential decay. So that brings us to the general form of an exponential equation here. You can see that we have what's called the initial value. We're calling that A, and then a growth or decay factor. So if this B right here, the base, if that is greater than 1, then when you change x, you're going to multiply by a factor that's greater than 1, which makes your function huge. That's why it's called growth. It's going to either do this, or if A is negative, it's going to go down because you're going to have that whole product there multiplied by a negative number, so it's going to go down. These are both growth functions, and a lot of students have a hard time understanding that even though it's going down to negative infinity, that's a growth function because the numbers just keep getting bigger and bigger and bigger even though they're negative. The magnitude of the numbers grows. All right, so what else can happen? Well, what if that base was a fraction? So let's pretend like a is equal to 4 and then b is like a half, and we raise that to the x power. That means that we'll have 4 times a half, and then 4 times a half times a half, and then 4 times a half times a half times a half, which means that every time you multiply by a half, it gets smaller and smaller. That's going to create a function that looks kind of like this, and that's our decay. Keeps getting cut in half, gets closer and closer to 0. That's what happens when b is between 0 and 1. Okay, so we have growth functions here. If b is greater than 1, the graph will grow away from the asymptote as you move left to right. That's pretty much the domain. We've done a lot of domain and range. So the domain here is going to be all real numbers. And the range in this specific example is y is greater than 0 because there's an asymptote there. It'll never equal 0, but it'll always grow away from it. All right, what else we got? Don't forget, let me back it up. Don't forget that this is also possible when a is negative because you have that product and it's multiplied by negative, it goes down. These are both growth functions. Decay functions, they get closer and closer and closer to some asymptote. In this case, it's y equals 0. The domain is all real numbers, and the range here is y is greater than 0, and that's when b, the base, is between 0 and 1. Okay, remember growth and decay. Don't forget about their negative functions as well. This is also what? Is that growth or decay? Now, a lot of students will say, well, it's going up, it's growth. Well, there's an asymptote there, and it gets closer and closer to 0. I didn't really draw that the best I could, but let's pretend like it never hits 0. It's actually decaying because the magnitude of these numbers is getting smaller, 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 but it'll never surpass y equals 0 there. So that's a decay function. What? Blowing my mind. Sometimes students have a hard time with that. It's getting smaller and smaller and smaller. So, long story short, if the graph goes away from the x-axis, it's growth. If it goes towards the x-axis, then it's decay. Easy enough? That's our summary thing. So let's look at these right here, and we're going to figure out whether they are growth or decay. Remember that all of our functions must be put in the form y equals ab to the x for us to figure this out. So we have to put them in that form because some of these won't be in that form initially, and we'll move them around. So let's look at this. What do we have here? First example, we have 1/2 is a, and then 2 to the x. Well, b, that's that number right there, is greater than 1. So that is definitely a what? That is going to be a growth. Neat. How about the next one? The a here it's positive, but we see that b is a half, so that's going to be decay. Let's look at this graph right here. This graph is going closer and closer and closer to 0. That would be a decay. How about this one here? Now, this has been translated. So this is getting closer and closer and closer to y equals 2. Now, we don't have to, at this moment in time, worry about what the equation of that function is, but this is also a decay function because it's getting closer. Basically, we took that decay function and moved it up 2. Remember how to do that? You add a plus 2 at the end. Easy enough. How about the next one? We have this function, it's going down, 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 down. If I trace it back up, you can see there's an asymptote there. That is actually a growth function. And how about this one here? Is there an asymptote? It doesn't really, is y equals 1, is that an asymptote? Let's pretend like it's not. This is just going higher and higher and higher, and it'll just keep going higher and higher. Okay? Well, that would be growth. There'd be decay. Would it be decay? No, actually, this one is, I got to get out my typing for this one. This would be neither. Kelly always does that. He just throws a neither in the middle. It's nothing because I'm assuming this just keeps going up and there's no asymptote. Now, if you made the argument that there's an asymptote there and we really don't have a lot of information, you could probably argue that it could be decay if that was the case. All right, how about the next one? It's just an equation. Now, this equation here, what you have to remember is that we have to get it in the form y equals ab to the x. All right, so I'm going to rewrite this one. So this is going to be y equals negative, let's see, 2 to the negative 1 raised to the x, right? Because our exponents rules say that this is the product rule. So we multiply those two, we can get that. So kind of, I'm going to take that x and put it up, and it's going to leave a 2 to the negative 1. So that's going to leave a different equation here. This is going to be like negative 1 times 2 to the negative 1. That's just 1/2 to the x. So this equation here is equivalent to this equation, which I put in the form ab to the x. And here you can notice that the 1/2 is what b is. The base is 1/2, so this is going to be decay. That's a tricky one. Let's try this one. Well, remember that negative right there? We're going to play the same game. So this is going to be zero point 0.4 times 7/10 to the negative 1, and we can raise that whole thing to the x power. And then we're in the form ab to the x. But having a negative 1 exponent on a fraction, that puts the 7 in the bottom and the 10 in the top. Remember our rules there? There'd be 7 in the negative 1, 10 to the negative 1, but then they switch. So this is going to be equivalent to 0. 0.4 times 10 over 7, and then that'll be raised to the first power, and that's raised to x. So we get x right there. So y equals 0.4 10/7 to the x. That's greater than 1, so this is going to be growth. Growth. So those two are tricky there. Let's look at this one. This is obviously growth by looking at it. Because it's going up, 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 up forever. It's just been translated down to, so there's probably a -2 somewhere in the equation. And the last one, what do we have here? X squared. That's neither. Remember, the x has to be in the exponent, so that one there is neither. Kelly, always giving us that last one doesn't work. All right, let's move on. That is determining if a function is growth or decay. Hey, there's our answers. Awesome. So now we're going to graph these. Now to graph them, what I would recommend doing, we're going to make a nice little graph here. You know, a lot of these, most of these actually center around the y-axis and the x-axis, the origin right here. But most of them are centered on the y-axis. So what I'm going to do is I'm just going to fill out this chart the way we normally do. You can put this in your calculator, or you can just kind of figure it out here. If I rewrite this equation using the same rules I just did before, this is the same as 3 times 1/2 to the negative 1, and that's all raised to the x. Right? So that would be the same as, if I write it over here, y equals 3 times 1/2 to the negative 1 power. That flips the fraction, so that's going to give us 2, and that'll be raised to the x power. All right, so that's our equation. All right, so fill out the table, pause the video if you need to, fill the graph out. I would put this in the calculator and then just go to the table in the calculator. Or if you want to do it by hand, because you don't have a calculator, you can do 3 times, I'll do the first one here, 3 times 2 raised to the negative 2 power. Well, 2 to the negative 2 power is 1 over 2 squared, remember. So this is all going to equal 3 over 4. So that's where that first number comes from. If you plug a 0 in, I'm just going to go through this quickly. Plug a 0 in, anything in the 0 power is 1, so that's going to be a 3. Plug a 1 in, that's easy, it's a 6. 2 in is 12, so on and so forth. I get this nice graph here. We have an asymptote at y equals 0. It'll never touch that number there. The domain for this function, well, I'm just going to call it all real numbers. If you want to use inequality notation here, we can say from negative infinity, x has got to be greater than or equal to, greater than or equal to, there you go, that's all real numbers. In the range here, y will have to be greater than 0. Or we can go, how's this work here? So 0 and then up to infinity. Booyah. So that's how we do the domain and range for this function here. Is it growth or decay? Anybody? Tell me. Growth or decay? Anybody? This would be growth. Okay, because if you notice, it's going away from the x-axis, away from y equals 0. Easy enough. Before we move on, let's get our next joke from Mr. Bean in Ramstein.
Well, hello there. Howdy-ho. This is Mr. Bean in Ramstein, and here's my joke. What kind of pizza do you get if you want it to be extra cheesy and 10 minutes late? A cheesy breast. 10 minutes late, cheesy breast. Mr. Bradley knows what I'm talking about. Have a wonderful new year.
That is fantastic. That's an amazing joke, Mr. Bean. All right, so next part, we're going to talk about interest formulas. We have 2 different types of interest. We have compound interest and then continuously compounded interest. And I guess the difference between the two, if you compound continuously versus if you compound at several times throughout the year, we have to use a different formula. In fact, basically this formula here is when you take the compound interest formula and take n to infinity, you basically get PE to the RT. But that's in you can look that up in Algebra 2 if you want to. Basically what you have to identify in these type of problems is, first, what type of interest are you doing? Are you doing it several distinct times throughout the year or over a month or something like that, or is it compounded continuously? It'll have to tell you that, and we're going to give you these formulas. So here we go. If you deposit $3,000 in an account that pays 3.28% annual interest, how much would you have if the interest was compounded daily for 5 years? or continuously. So we're going to use two different formulas to do this one. So first we'll do the daily for 5 years. So here's a formula. We're going to write it out. So A equals P times 1 plus, it's the interest rate over the number of times it's compounded, times NT. Now T is the time in years, how many years. So this is a 5 years. We're going to plug a 5 into there. The rate, you have to write it as a decimal. So you plug that in as point. We're going to say R equals 0.0328. All right, plug that in there. The number of times per year, it's compounded daily, so N is going to equal 365 here. We'll just assume there's a normal year. So what do we get? Principal, how much you start with? So A equals 3,000 times 1 plus, and then we plug in the 0.0328 all over 365, and we raise that to the NT, so that'd be 365, and time is 5 years. When you work all that out, what do we get? I get $3,534.62. All right, so that is the compound interest formula when you have a distinct number of times that you're going to add that interest. In this case, it's compounded daily, which means every single day. Let's do the next one. The other form is actually a little bit easier. So we have A equals the principal e to the RT. So in this case, what do we get here? 3,000. And then E, remember that's Euler's number, raised to the 0.0328. We still want that as a decimal. And then how much time do we have in this problem? Still equal to 5. When I work that all out, we get your total amount to equal, what do we get? 3534. So that's pretty close to the other one. Whoops. Point, that's a regular number there, 64. So you get a little bit more money there, compounded continuously. So which one's a better deal? Well, in this case, continuous is a better deal for you. So that is our interest formula. There's one example of each. Not too difficult. You just plug it in, figure it out, use your calculator. There we go. Next problem. All right, the next problem, growth and decay models. This basically takes us back to what we were doing before. Remember, 1, if this were a 1 here, remember it's a, b to the x. Well, we're just changing some of the variables. X becomes a t. But if this were a 1, nothing would change because it would be times 1, times 1, times 1, times 1, times 1. And so remember, if it's greater than 1, then you have an increase. That's a growth. And if it's less than 1, it's a decay model. All right, so let's look at the different variables we have right here. T is time, not necessarily years here. It could be hours, could be minutes. A is the initial value. And what do we have? What do you got? You add if it's a growth, and you subtract if it's a decrease. What is y there? Why is the total amount that you have? All right, so it's the amount of whatever you have. It's the amount you have. Remember, the A is the amount that you start with. That's the initial value. So let's do number 5 here, the relative growth for bacteria. Sully's tongue, relative growth, 80% per hour. So it grows at 80%. Does that mean that it's going down or is it going up? Well, that means it's going up. So basically, let's write this formula out here. So we get y equals, hey, how'd that happen? That's crazy. Y equals a, 1. In this case, we're going to do plus. We're not going to do minus, and it's going to be raised to the t. So we get, what do we got? 80% after eating a Turkish pizza. Let's break this down. So what is the rate of growth? 80%. That's easy. So that's going to be R. R equals 0.8. That's 80%. We write it as a decimal, like we did before. Swabs his mouth, starts a culture 4 hours later. So T, that's going to be T right there. So T is going to equal 4. That's awesome. And at that moment in time, that's not how much he started with. At that moment in time, there's 50,000 bacteria. So that's what y is going to equal right there. So the amount 50,000 is going to equal some value of A. By the way, that's what they're asking us. How many bacteria did he start with? So we want to solve for A. So 50,000 equals A times 1 plus 0.8. And then how many hours? 4. So to solve this, you could do inside the parentheses first. So we're going to get what? 1.8 to the 4th power. 1.8 to the 4th power times A. You just divide each side by 1.8 to the 4th power. I have no idea what that number is off the top of my head. but your answer is going to be A equals 50,000 divided by 1.8 to the fourth power, and that should give you somewhere in the realm of 4,763 bacterial. That is approximately what A would equal, so that's what you're starting with. Ta-da! And there's that. By the way, speaking of Sully, time for a Sully joke.
Hey, this is Mr. Sullivan at K-Town. Here's my joke. What's too long, terrible, and should have stopped a long time ago? This video. Happy New Year, everyone!
Yes, but how do you really feel? That's what I want to know. All right, so let's do the last couple. I'm going to do 2, and then you can do number 8, and then we're all done. So, solving these exponential equations here, they have exponents all over the place. We just have to remember our rules. Remember our rules for simplifying? So let me show you what that means here. What do? I see a 3, I see a 9, and a 27. That's going to give me a hint here. So I'm going to rewrite this. This is 3 to the x squared in the numerator. And on the bottom, I'm going to rewrite that with a base of 3. So that's going to be 3 to the third power, right? 3 times 3 times 3. And over here, we're going to have a 9, which is really 3 squared, right? And that's raised to the x power. So all I did was take all those numbers, and I noticed they are all powers of 3, so I rewrite them that way. Now I have my properties of exponents. That says when you divide the quotient property, you have to subtract exponents. So this is going to be 3 to the x squared minus 3. And that should equal, and then the power property, is when you multiply the exponents, so we're going to get 3 to the 2x power. Well, guess what? We have 3 to some quantity here is equal to 3 to some other quantity. These quantities have to be equal to each other. So at this point, I can just say, hey, x squared minus 3 has to equal 2x. And at this point, it's a quadratic equation. You can move things over to one side and then factor it. I'm not going to make you go through all that stuff. You should get -1 and x equals 3 when you're done doing that. Does everybody understand? You remember how to factor? You should. We're in pre-calc. All right, number 7. Same idea. I look at all these powers of 4. This is really ugly, though. I'm going to rewrite that. That's 4 to the third power. And then that. You got to be really careful with your parentheses and everything. So that is raised to the -3w power times, what is this, 1 over 4 to the third, so that's 4 to the -3, and this is all equal to the 4 squared power, right? So 4 to the -3, did everybody catch that? So that's 1 over 4 to the third, which would be 1/64th, so that's where that comes from. So at this point now, what am I going to do? I'm going to multiply those exponents, so 4 to the -9w times 4 to the -3 is going to equal 4 squared. At this point, remember our rules when they're side by side here. This is the product property. You can add those together. So we're going to get 4 to the -9w minus 3. I just added those together. You can do plus -3. That's going to equal 4 to the second power. And we have the same situation we had before. We have 4 to some quantity is equal to 4 to some quantity. That means this thing has to equal a 2. Because they're equal to each other. So we're going to get 9w minus 3 has to equal 2. So we add 3 to each side. We're going to get -9w equals 5, or w equals -5/9. How crazy is that? Cray, cray. All right, you try number 8 all by yourself. Go. Pause the video. Okay, let's hope you get the same thing that I'm going to get here. All I did was rewrite 16 is 4 squared, and this is 4 to the -2 power. 1/16, right, for the same reason as this up here, and 4 to the first. So at this point, I'm going to multiply. You just have to you have to be careful because it's quantities. It's 2 times this whole thing. So 2 times 2r plus 3. And then, let's just should we figure that out? So we get 4 to the 2 times 2r plus 3 times 4 to the -4r, and that should equal 4 to the first. All right, so that's 4 to the 4r plus 6. And then, what do we get here? Times 4 to the -4r. I'm just going to write it out again. Hey, no reason. It's brand new year. Take our time. Now the rule is you add these together. Well, the 4r and the -4r, they cancel out. What? You're going to get, what do we get? We get 4 to the 6 equal to 4 to the first. When is 4 to the 6 going to equal 4 to the first? That means 6 has got to equal 1. Say, what? No solution. Kelly did it again. Truly! Every time I give you one to do by yourself, it's no solution. Why would that be? But that's basically how you go about that problem. 4 to the 6th will never equal 4 to the 1st. It's no solution there. All the variables dropped away. Hey, this is Mr. Kelly in K-Town. Hope you have a fabulous new year, and we will see you in 7.2. Good luck. Mr. Kelly in K-Town. Remember, it's nice to be important. More important to be nice. See ya!